So, I'm going to talk about, despite my expertise in the optimizers, now I'm going to talk about vacuum and statistics that have been proposed 2 years ago, and now it's developing. That helps us to understand how your vacuum works in your system, and it helps us to estimate the efficiency of the system, and it can provide some useful information to adjust settings for it. So it's really important. And okay, how does it work? Down? Okay, yeah. So first and foremost, I explain to you what the problem have been solved and why this idea, why it is important for us. Just in case, I'll show you 3 prototypes. There were 40 prototypes, but the second and the third prototypes are similar, so I cut down them to 3 prototypes. And I'll explain to you why we have rewritten them and what feedback we have got. And I'll show you how we can use them and how these statistics are correlated to vacuum parameters. And we'll make a conclusion. Some information about me. So I'm a core developer with 5 years experience, almost, and I have been contributing in Postgres community since 2023. Yes, and so for now I have been working with optimizers, but with statistics too, because they are closer to each other and they are dependent. They're related to each other. Okay, and so because of this, I have been working with vacuum too. And so the main idea and the problems that we have. First and foremost, we need to remember why the vacuum is so important for us. It helps us to reclaim the space, to store more tuples. And because of this, we need something that helps us to delete old versions of our tuples. And besides this, vacuum helps us to update the visibility maps that is important for indexes, and it can accelerate the index processing, and it updates information about free space map. It freezes tuples, blocks, tables, and update catalog information. So it's a really important system. And we have some difficulties. One of them is related to the fact that long-running transaction can prevent vacuuming such tuples, and there might be a problem with bloated indexes or bloated tables too, and because vacuum doesn't have time to reclaim ours, to delete old references on dead tuples or clean up them. And there are a large number of parameters, and not only the whole system, but for relations, for example. And it's really difficult to understand how they influence on our system. And because of this, we need statistics to understand it. So it's a problem for us. DBA, it's like DBA needs to monitor its system frequently. And we have like an idea how to make his job simpler. For example, he can start auto vacuum, or okay, not auto vacuum. He can start vacuum, for example, for the whole database, or after vacuum works automatically without his attention, and he needs sleep because he is a human, and he wants to open only some report about statistics and sees some anomalies that helps him to understand that some objects needs his attention immediately. For example, such anomalies you can see like pigs. Oh, it's like on the right of the slide, and it means that something is wrong, or maybe wrong with your system, and we need more closely see our objects and its statistics to understand what happened, and adjust settings for them, or maybe provide vacuum for sort of things. So, but there is a problem that it should look like this. So cumulative statistics system in the PostgreSQL gathers and saves such information for us, but it does not collect information about vacuum, unfortunately. Or it collects only a small part of this information. And with such a system, we can build some reports that visualize our graphics, or it can be visualized with tables, and it can show us how dynamically our system changed. And there is a problem now, because PG-Statal tables provides only few information about this. It can provide you how, it's like how often your vacuum vacuumed your tables. It's like number of vacuums or auto vacuums. How many dead tuples it removed, and what the time was for last vacuum for your relations, for example. And the recent statistic was about time. It's like how long your vacuum was during the period, for example, of the period, because it is cumulative statistics. And there are no information about I/O, wow, I mean vacuum. And PG-Stat progress vacuum, it's another view that can provide more information about vacuum, but it's really useful to understand why your vacuum lasts so long. For example, you can attach to the process and understand what's the current phase of this system, and you can find some counters. It's like some statistics about this, but it doesn't store any history about this. And server log, so it provides all information that our cumulative statistics stores, but it's really difficult to parse it, and it requires some memory to solve it, because it's there are files with such logs. So 3 prototypes. First and foremost, we need to understand how our vacuum works. There are 4 steps generally. First and foremost, vacuum vacuum scans the table to collect some dead raw versions of tuples, and after that, before it cleans up them, it needs to remove index references on this on these tuples, and it's 2 stages step, and I will explain it why it is important. And after that, it removes the tuples from the heap, no, from the table. And the last stage is truncate the table. It means that it removed some empty pages after its work, after it finishes its procedure. And so every stage can provide us useful information about vacuum. First and foremost, we can collect information how many pages we scanned, not we, vacuum scanned, to find such tuples. How many tuples it freezes before it was ready to remove them, and how many index pages it scans in its the second step, and some information about val. It's important for the systems, and I/O information. And about as for truncation, it provides some information about pages removed. So these statistics show us how vacuum was useful for our system and how efficiently it worked. And it explains how my patch works. Before the step starts, we need to take a snapshot. Snapshot is like the value of our statistics, and after our step, when our step ends, we need to take another snapshot, and the difference between the second snapshot and the first snapshot shows us how many vacuum processed pages or tuples, or how many it could delete them or did not delete them. And due to the fact that it's at these stages split it in due to the fact that before removing tuples from the heap, it's stable, just in case. We need to remove references on this tuple, so because otherwise it would lead to crash our system. And because of this, we need to take 2 snapshots too for indexes. And after we take the last snapshot, we are ready to report such statistics in the cumulative statistics system. And we need to exclude index statistics from the heap statistics, because based on the vacuum design, index processing is inside the heap processing, I mean, when vacuum processes the heap. So, and as for statistics, there are some common statistics for indexes and tables, and it includes buffers, vals, and time statistics, and wraparound fail-safe count, and interrupts. It's like only because due to the fact that val and I/O statistics are global for us, we need to be careful for them, because of excluded stage has been added here because of parallel indexes, parallel vacuum. It processes it in parallel way. And there are only heap-only fields. It means that only for tables. It includes pages scanned, pages removed, tables deleted, tables frozen, or tuples frozen, how many pages have been set as frozen or visible, or or vacuum did not clean up such tuples for some reason. For example, it did not require, or it did not hold the lock on the index because of another transaction that did not allow him. And because of this, we collect information about recently dead tuples, misdead pages, misdead tuples. So it can say us that this table is so frequently updated, or maybe something wrong with them, or with it, or sort of things, and we can adjust our settings because of this. Or system as whole. And as I mentioned before, we store such information in cumulative statistics, because it was built for that. And but as for cumulative statistics, it's important one, besides all these objects, the most important object here is pgstat shared hash table. It collects information what kind of object stores such statistics. It can be a relation, function, database, or, for example, our specific custom statistics. It shows us what database, in which database this table is located, and the object itself. And it's important for us, and our initial patch was built based on this design. So there is a structure to store in statistics about relations, and it is called pgstat tab entry, and we added extra field there, vacuum statistics. And because our vacuum statistics belongs to relations, tables or indexes. And because of this, we chose this path. And but it faced some feedbacks, negative feedbacks. First and foremost, there was a bloat for every table because we allocated full space for vacuum and for statistic tables itself, or relations itself. And despite the fact that we are ready to collect, to gather such information about vacuum, because architecture of design does not allow us to exclude such allocation memory or particularly allocated it. And there are no control or filtering because we want to gather statistical information only for particular object, for example, or gather information for special statistics, for example, only for val. But it did not allow us to use to realize it without excessive code and changing architectures and so. And because of this, we tried to explore another approach for us, and it was related to add more, 2 extra slots in cumulative statistics system, despite for relation. And we have named them pgstat kind vacuum DB and pgstat vacuum relation. And so it works like any statistics, but this approach required a lot of more codes, and filtering design was not accessible for us anyway. And there was a suggestion for us: can't we do the same? Like, can't we do this like PG stat statements? No, so we can add an extension that provides us to control, to gather vacuum statistics, and it can be helpful for us. And we realized it through two custom kinds statistics. So, and our most of our code and some extra code for filtering was written in the extension. And it helps us to cut down overhead, because if you don't load an extension, you don't want to store such statistics. And so it was brilliant for us. And it works like any statistics, but it is custom statistics. So it's like we use our cumulative systems like before, but it is available for us only if we load extension. And as I mentioned before, we added filters. For example, we have added filters what we want to track. Like, for example, we want to track only tables or only indexes or only databases. It means that statistics gathers anyway, but the extension makes the decision based on the GUCs. It will be stored in the cumulative statistics storage or not. And for example, sometimes we want to collect information only about buffers, vals, or general statistics. So now it's available. Or for example, we want to collect general statistics about vacuum only for database. So it's available too. And sometimes we want to collect information, vacuum statistics only for particular objects. Like we have a list of OIT objects, for example, special relations that are heavy for us, for systems. And so they only for these particular objects, vacuum statistics will be saved. And we have received feedback from Andrei Borodin. He said that, he said particularly about delay time, and he said that we are on the right way. And we have had a critic from the developer, and we included I/O and val in our total time, and it is not acceptable for us, and we should exclude it. And it is open issue for us. We didn't figure out how to solve it. And there is summary diagram about third approaches. And so, how to use vacuum statistics? First and foremost, I would like to share with you about PG profile. It's an extension, open source extension, that helps us to show you statistics in more convenient way. It takes snapshots. Or for example, you can see the line, and you can take snapshots like S1, S2, S3, it's all snapshots. And the difference between snapshots from S3 to S1 shows you shows you how dynamically changed our system between these two periods. And it could provide you how your system have been dynamically changed over the period. And for example, you can see vacuum time over the period, or how many useful vacuum was in terms of updating visible map marks, or I/O systems, or how statistics have been changed in buffers, for example, or cached. And so, for example, there are two databases here. One of them have been frequently changed. It's PG profile, and another one is Pulsar. Have been dynamically changed is Pulsar. Oh, no. Yes, it should be Pulsar. It should be switched from green to orange. Sorry for that. It's like now it shows like PG profile is frequently changed, but it should be a Pulsar. And PG profile it has small changes, and because of this, you can notice that if database have small changes over the time, vacuum time is too small, so it's almost zero, sort of. But as for most frequently changed database system, you can notice that vacuum it's nearly worked, or its work time increased significantly, or it cuts down again, and sort of things. And this file shows us, now it's correct, sorry, it shows us that how vacuum was useful, and it shows us between the balance vacuum as a system in our database system, because this picture displays us the diverse. No, 1 second. It's like it explains us two statistics. Vacuum when set frozen pages on the tuple, it set marks like this, but the backend can unmark such tuples when it needs to read them, or provide information for them, or sort of things. And so because of this, the diverse, between these two statistics can show us is vacuum so aggressive for our table or not. For example, if this point is almost zero, it means that our vacuum so frequently set pages as frozen. And if it is so high, it's almost 100%, it means that our there are a lot of number of operations when backends unset such marks, and it means that we need to find a balance for aggressive parameter of vacuum. And another statistics shows us how about delay parameter of vacuum. So these statistics show us total time of vacuum and delay time. And if you can notice that they are almost balanced, because mostly. It means that despite the fact that vacuum work. It needs it's mostly 10% of time all over this to sleep, and 70 maybe 75% of time, and so it helps us to adjust settings about delay of vacuum. And another, and you can notice that block reads yes, nope, 1 second. Yeah. Statistics about block reads and total time are related to each other. Okay, mostly. And block read time you can shows us what tables requires more attention for vacuum in terms of work, and it can help us to understand what time of contribution vacuum, what time of contribution of the total vacuum time was on scanning blocks from the disk. And based on the statistics, it's like how much time vacuum spent for relation can ask you about the trend of activity of vacuum. For example, you can notice that despite the peak, it means that the operation the vacuum operation have been finished, and because of this peak, you can notice that in the rest of the time, vacuum is almost silent, or sort of. It's like it did not spend a lot of time to process our tables, and mostly it happens on weekends. And now we are going to play in detectives, and so there are block reads, and you can notice that cache block reads is falling down, but cache hits is increasing. It was unexpected for us, and we tried to investigate what was wrong with our system. And so we took two snapshots between two intervals to understand this, and there is a table that provides information about this. And you can notice that from 6 million, the number of read blocks cut down to 2 million for this table, and total vacuum time decreased by third time, and I/O read time decreased too, and so it's declining. Mostly means for us that something is wrong, and such objects needs our attention immediately. And we tried to investigate which tables made contributions to our database. And so you can notice that QRTZ triggers, the first table, vacuum spent on it most of the time. And you can see that it read most of the part of the blocks that we detected before. But at the same time, you can notice that the percentage of hit has been decreased too. And it's interesting about us what happened anyway. And we continued our exploration. And we detected that for indexes contribution too. We can see that hitting rate has been increased too here, and our investigation ended up the fact that some queries have been executed by the backend, and some pages have been added in the buffers. And because of this, Vacuum used them instead of read blocks. It caught them or it got them from the cache. And you can notice that there are the same reads accumulatively that make the contribution for this. And I was playing with the parameters of Vacuum to understand how they influence on our statistics. And the test took 1 hour or about it. And first parameter that I took was maintains work mem. I took the significantly lower number of memories than it was by the default. And you can notice that after fixed parameter, when I used default parameter, the vacuum vowel bytes reduced significantly, and but despite vacuum time. Okay. And another problem was, I called it like passive auto vacuum. But let's consider the first case. And so the test was provided on the PGBench database, and you can notice that with workmem parameter, decreased workmem parameter, Vacuum spends more time, significantly more time on the table. And it scanned more pages, and it provided significantly less its efficiency. And so it means that such statistics can help us to understand it's like despite it's like imaginary high imaginary efficiency of Vacuum based on the read blocks, it's really useful to see how many tuples have been deleted from this. And it can help us to understand what such parameter about memory can be improved. And as for memory, it means for Vacuum that it's a capacity for Vacuum to gather tuples that will be cleaned up after that. And if it is a small capacity, Vacuum frequently will be returned to this table, and because of this, it would spend more time than with increased capacity for this. And another parameter was delay. I increased it by twice. And you can notice that Vacuum total time decreased significantly, but mostly Vacuum sleep. And so you can see that after fixed parameter, the Vacuum total time cut down significantly, and pages scanned remains the same. So we are ready to make a conclusion. So we have such statistics to make DBA work more simpler, and now our pipeline works. Vacuum statistics helps us to monitor our system, find some problems or problem objects, estimate the vacuum efficiency, and it helps us to understand vacuum system. And there is a difference between the current stage and what our extension provides in terms of statistics. You can find my patch here. It is called Vacuum Statistics, and on the Commit Fest. So vacuum statistics was written not only by me, it was written by my colleagues too. So Andrei Lepekhov and Andrei Zubkov, but extension I implemented. So thank you very much for your attention, and I'm ready to answer your questions. And sorry for delay.